Hello everyone and welcome to Linked List Under the Hood. Today we are going to build dynamic data structure from the ground up, starting with one of the most fundamental one, the linked list. As you can see from our visual here, a linked list is essentially a series of connected blocks where each block contains some data and points to the next block in the sequence. We'll explore what this means for how we store and access information. To truly understand a linked list, let's use a simple analogy. Unlike an array, which is like a parking lot where every car has its own numbered spot, which you can access directly, a linked list is like a train. You can't just teleport to the 47th car in the middle of the train. You have to walk from the engine, car by car, following the couplings. This brings us to a core rule. There is no random access in a linked list. You must follow the connections or pointers one by one, giving us the sequential access. The big trade-off here is that while looking up a specific item might be slower, we gain incredible flexibility. We can easily add or remove cars without rebuilding the entire train, leading to a very efficient insertion and deletions. So why not just use arrays all the time? Arrays are fantastic because they store elements in a contiguous block of memory. This means all of your data is nicely packed together. However, this contiguous nature becomes a problem when you need to insert an item in the middle. For example, if you want to insert a new element at index 4 in a full array, you'd have to shift every single element from index 4 onwards to make space. Imagine doing that for a very large array, say moving 999,999 elements just to add one item. That's a huge bottleneck. An operation with O(n) cost, where n is the number of elements to shift. The solution to this problem is the node. The node is the fundamental building block of a linked list. Each node is typically divided into two main components. First, we have the value or data. This is where you store the actual information, which can be an integer, a string, an object, or anything else you need. Second, we have the pointer, often called next. This is a reference to the next node in the sequence. It's how one piece of our train knows where the next car is, a crucial node. If a node's next pointer is none or null, it signifies the end of the list. It's like a train car sitting alone, not connected to anything further. Building the chain is where the magic happens. While we draw them side by side, the computer doesn't actually store linked list nodes physically next to each other in memory. Instead, it only needs to know where the head of the list is. From there, each node contains the address or the reference to the next node. For instance, node 1 only knows about node 2. It has no direct knowledge that node 3 even exists. This brings us to a very critical point. If you lose the head pointer, your entire list becomes unreachable, and the garbage collect will eventually eat it up, meaning that memory is freed up because there is no way to access the data anymore. Now let's talk about traversal, or what we can term as the linear walk. Because linked lists are not like arrays or like index dissects, there is no shortcut like list bracket 100 to jump directly to the 100th element or 101st element. To find a specific item or to reach a certain position, you must start at the head and step through each node sequentially. Head, then head.next, then head.next.next, and so on until you reach your target. This linear walk means that finding an element in a linked list has a time complexity of O(n), where n is the number of nodes. There are absolutely no shortcuts here. But here's where linked lists truly shine. The superpower is insertion in O(1) time. Let's say we want to insert a new node with data 99 between node A and node B. We follow a two-step process. First, we identify the insertion point. Then, for the require new step, which acts as our safety net, we make the new node point to node B first. This ensures that we don't lose the rest of our list. Only after the new node correctly points to node B do we link old, which is like the snip. We then make node A point to our new node. This is a very cheap operation, requiring no shifting of existing data, just the change of two pointers. That's O(1) efficiency. Deletion is another area where linked lists are very efficient, often referred to as the bypassing act. When we want to remove node B from our list, we don't actually delete node B directly in the code. Instead, we simply bypass it. We tell node A, hey, the previous node, to point directly to node C. Once node B is no longer pointed to by any active part of the list, it's cut loose and becomes unreachable. At this point, the system's garbage collector will automatically reclaim the memory that node B was using. A crucial note here is that to perform this bypass, you need access to node A, the node immediately preceding the one you want to delete. However, singly linked lists do have a limitation. They are a one-way street because each node only points forward to the next. If you are traversing the list and accidentally overshoot your destination, you can't simply step back. You'll have to restart a traversal from the head, which can be very inefficient. This unidirectional nature makes operation like undo or reversing the order of the list much more difficult than they might be with other data structure. To overcome the one-way street limitation, we have the upgrade, doubly linked list. In a doubly linked list, each node includes an additional pointer, usually called prev, which points to the previous node in the sequence. This means that each node now has prev, data, and next components. This upgrade gives you total freedom to move both forward and backward through the list, making it incredibly versatile. This structure is great for things like browser history, where you might want to go back and forth between pages, or music playlist, where you skip forward or rewind. The trade-off, however, is higher memory usage, as each node now requires twice the number of pointers. Beyond standard linked list, we also have something called as a circular list, which introduces the loop. In a circular list, the tail of the list, or the very last node, instead of pointing to null, connects back to the head of the list. This creates a continuous loop. Circular lists are useful for scenarios like round robin CPU scheduling, where tasks are processed in a cycle, or a board game turns. However, there is a significant warning. Standard traversal loops, which typically check while next is not null, will run forever in a circular list. You need to implement specific logic to detect when you have completed a full cycle in order to avoid infinite loops. Let's summarize with a battle of the structures. Arrays versus linked list. When it comes to accessing element by its index, arrays are the clear winner, with O1 constant time access. Linked list, as we discussed earlier, require a linear walk, making it an ON operation. However, when inserting an element at the head of the list, linked lists take the win with the O1 efficiency, as you only need to adjust a couple of pointers. Arrays, on the other hand, require shifting all existing elements, making it an ON operation. Similarly, inserting in the middle of a linked list is O1 if you already have access to the node where you want to insert. Arrays still require ON for middle insertions. So, arrays win on random access speed, while linked lists excel in structural flexibility and efficient insertion and deletion, particularly at the end of a specific points. Now, for a quick reality check under the hood regarding memory and cache. While theoretical big O notation is important, it doesn't tell the whole story, especially when it comes to modern computer architectures. CPUs love contiguous data, which is what arrays provide. When an array is accessed, the CPU's cache can prefetch nearby data, leading to cache-friendly access and faster processing due to locality. Linked list nodes, however, can be scattered throughout memory. This means that when the CPU reads one node, the next node might be in a completely different memory location. This constant jumping around causes cache misses, which forces the CPU to retrieve data from a slower main memory, making linked lists in practice slower for sequential access than arrays, even if their big O for certain operations seems similar. Finally, let's talk about can I speak today about an important interview pattern called the runner or two-pointer techniques. This technique involves using two pointers that traverses the linked list at different speed. You typically have one pointer, often called the tortoise, moving very slowly, one step at a time, and another pointer, the hair, moving fast, usually two steps at a time. This pattern is incredibly useful for solving various linked list problems, such as finding the middle node of a list or detecting if a cycle or loop exists within the list. To wrap up here, the engineer checklist for when to choose between an array and a linked list. First, ask yourself, do you need random access to elements? If yes, use an array. If no, consider the next question. Will you have frequent insertion or deletions, especially in the middle or at the head? If yes, a linked list is likely a better choice. If no, then consider if you have strict memory constraint. If yes, an array might be preferable due to its potentially lower memory overhead compared to a doubly linked list. For example, the key takeaway is this: there is no single best data structure. The optimal choice always depends on the specific requirements and constraints of the job you're trying to do. If you like the video, please do like, share, and subscribe. Thank you.